Alright, here in section 4.3 we're going to extend our knowledge about probability to a couple of other questions. And the first thing that we're going to look at that's contained in this section is what's called conditional probability. And conditional probability can be explained in a lot of ways, but essentially what's happening is a condition is being put on. And what I mean by that is, because of that, you are not looking at all the data. Right? You know something about it, a condition's been put on it, and so you limit your focus. And so a notation for that is something like this: the probability that B happens given A has happened. This is the probability of B happening given A, right, is a way to read that. So if you ever see that notation, I just wanted you to appreciate that as the conditional probability. So what I took the liberty of doing is translating out a table that we used in the previous section. You'll use a pretty similar table as you're in the homework as well. And so conditional probability is best answered from a table point of view. And so I'm going to erase these definitions since you have the ability to back up and rewrite them. You could read what the book definition is as well. But let's come into this data set. And if you remember this data set from the previous video, there's 1,118 different pieces of data. So let's do a small review. We could ask a question like this: if one order is randomly selected, find, and then I'm going to put A. Oh, actually, let me do this a little bit differently. Find the probability that, and then I'll put A. The order is from Burger King. And what we have is a 4.1 problem. Right? That's a 4.1. One person being selected, no problem whatsoever. We can handle that. How many orders are from Burger King? Well, we can see the Burger King orders right there, right? When just making sure we're looking at the right areas. And that's 264 plus 54. And that's 300. Whoops. Did not go back to the pen. That's 318 orders that are from Burger King, and that's out of, if you remember, the total was 1,118. We totaled that up last time, but if you did a quick add of all those numbers, that's what we would have. So from a chart, we could ask a 4.1 question. Again, our book, the computer will probably want you to reduce. So if I divide by 2, I get 159, 559. And then I think that might be done. Oh, yeah, that might be done right there. So that might be the end answer to that. We could look at that in a decimal format. 159 divided by 559, and realize that this is 0.2844. So about 28% of the orders come from Burger King. So we could have another question, 4.2. The order is either not accurate or from Taco Bell. Okay, so let's think about that for a minute. Let me erase my highlights here. So if I come in here and erase my highlights, let's highlight what we want. We want the order to be not accurate. Let's go get all the not accurate orders. There they are, right at the bottom there. So not accurate. So let's see how many those are. The not accurate orders are 33 plus 54 plus 31 plus 13. And we have 131 orders that were not accurate. I'm putting that in yellow since I highlighted it in yellow. Now the question is and I'll come back in here and highlight in a different color, are there any that are from Taco Bell that we haven't already counted? These 145 are from Taco Bell and that we haven't counted. So I have to add in here 145 more orders. And that's still all out of 1,118 orders. So I take my 131, I add the 145, and come up with 276 over 1,118. And so that's 138 over the 559. And I think we're good there as a reduced answer. And so I could divide that by 559 and realize I got 0.2468, so 2.247. The other thing that could happen is a 4.3, but with it being, well, I apologize, 4.2 still. And that's going to be a different question. If 3 orders are randomly selected, find the probability that all 3 are not accurate. Well, we've already counted the not accurate ones. If you remember, that was the yellow highlighted. That was the 131. So that's 131 orders out of 1,118 when we first go in. So we want the probability of not accurate, and then not accurate, and then not accurate. And so the first one not being accurate is 131 out of 118. Now, we got that one, right? We are given that that first event happened. So now there's only 130 non-accurate orders over 1,117 orders left. And then there's 129 over 1,116. So just to do a brief review of all of those. So if I plug that in, 131 divided by 1,118 times 130 divided by 1,117 times 129 divided by 1,116. And I get a very low number, 0.001576, so 158 is how I would round that. So just a quick review of the first 2 sections and all the problems that are there. That leads us into conditional probability, which isn't bad. So I'm going to take a moment to come through and erase all of this, and then continue with our discussion of conditional probability. Okay, so what's the question going to look like for conditional probability? So you have that definition that I gave you earlier. You're given some piece of information. There's a condition that's already been met, and you're answering the question. So this is a conditional probability question. If one order is randomly selected, find the probability that it is not accurate given it was from Burger King. Okay, so the key word in here is the word given. The fact that it was given. So whatever follows the word given is something that you know. So what do we know? We know that this order was from Burger King. So how many orders were from Burger King? 264 plus 54, right? We're only looking at this column right here. Nowhere else. And so we're only looking at 318 orders because we know it was from Burger King. Out of the 318, how many were inaccurate? 54. So this is the probability that was not accurate given it was from Burger King. And we would take the 54 and divide it by the 318 to come up with a 0.1698. So if I round that, it would round to 0.170. So about 17% of all the Burger King orders were inaccurate. So let's compare that to, well, let's let's look at the other way. What's the probability that the order was from Burger King given that it was not accurate? That would be the symbols. Let me write that in words though. So find the probability that the order is from Burger King given it was not accurate. Okay, and so they'll ask different questions just like this, and it's easy. You just know that your focus is limited. So what are we limited to? What do we know? We want to know the probability that's from Burger King, but what are we given? What do we know? We know that that order is not accurate. That's what we know. So I'll highlight that's what we know. So we know it's part of this row right here. So how many are in that row? I don't know if you remember. So we'll quickly add them up and get our 131 again. So the number of non-accurate orders is 131. That's the only row we're looking at because we know it's not accurate. And then the question is, how many are we from Burger King? 54. So 54 divided by 131 is equal to 0.4122. So 0.412. So pretty interesting. So at Burger King itself, the first question is telling us that their percentage of non-accurate orders is 17%. What this bottom one saying is if you looked at all the inaccurate orders, Burger King would have a lion's share of them. They would have 41% of those non-accurate orders. So they seem to be more, they seem to have a higher rate of not accurate orders compared to everybody else. And so that's what given probability is. It just goes off of those types of settings. If we look at one more example of conditional probability, maybe it would be good to look at a drug test one like we did before. So remember we had a marijuana drug test. And sometimes that test read positive and other times it read negative, and sometimes the person used and other times they did not use. And so the test was right 119 times when somebody used and was wrong twice. When somebody didn't use, it was wrong 24 times but was right 155 times. Because if they don't use, they should have a negative result. And if you remember, there were 300 total people here. Well, we're never going to see that 300 used if we have conditional probability. So look at this. This is how they would find the percent accuracy of the test. They would say this: find the probability that a person tests positive given they used. So that's what the test is designed to do. That is designed to test positive if somebody used. And so let's see how accurate that is. The probability that somebody tests positive given that they used would look like this in symbols. And I'm just using the symbols in case they do in the homework. And so how many people used? Let's go find our users. We'll use the same yellow highlighter. What do we know? We know the person used. Why do we know they used? Because it's after the word given. Well, there's 121 that used. And out of that, 119 tested positive. So what is 119 divided by 121? Typed it in wrong. It is a 0.983. So this thing has about 98% accuracy from what it's designed to do. So they would say that it's a 98% accurate test. But it's messing some people up, right, that don't use, so it comes with some consequence. What if we found the probability that someone used given they tested positive? So you could look at it from that side. You could say, well, if it tests positive, I want to make sure that they used. I want to have a degree of confidence in that. Well, what are we given this time? We're given that they tested positive. And how many people tested positive? 119 and 24 more. It's for 143. So 143 people. Oops, let me write that lower. 143 people tested positive. How many used? Well, we know that's 119, right? We're only looking in that row. Don't count the 2 because those 2 people down there tested negative. So we take a 119, divide by 143, and we come up with 0.832. Now, through that lens, things look a little bit worse. A positive result has about an 83% accuracy rate. Well, that's not good in a way, because that means in not an unusual amount of times, not an unlikely amount of times, somebody that didn't use would test positive. So they better have subsequent tests and things. But this is how conditional probability is dealt with. Typically in tables, you're isolating areas and coming up. I think for the second part, I'll create a separate video so that it doesn't get too long.